Hi everyone, this is the second video together. In this video I'm gonna show you an experimental modal analysis performed on a VRIM by using an instrumented hammer, and therefore we're gonna perform an impact test analysis. The setup of this analysis is very simple, also with respect to the shaker analysis. So here we got our VRIM that is suspended with these elastic bands in order to recreate the free boundary condition. I have already discretized our rim in 36 points. There are some points along the circumferences of the rim, other points here in the width between the two flanges, and other points instead here on these faces between the spokes. Moreover, I have put the origin of the absolute reference frame, so our global coordinate system, here in the center of the rim, and I have already attached these three axial accelerometers in these 2 points. In this case, for this analysis, these 2 accelerometers will be fixed in this position for all the duration, for all the time of the analysis, because we will use the hammer for impact all the other points, and therefore we're gonna perform the so-called roving hammer analysis. This is the hammer that we're gonna use for the impact testing, and this is a special hammer, of course, because inside there is a transducer that can measure the force, and we can also remove the tip here of the hammer. This is a steel tip, but we got also other type of tips. For instance, in plastic material with different hardness, and you can choose it depending on the material by which it is made of the test structure. I want to show you also other type of hammer with different dimension. This is a very small hammer that can be useful for micro vibration analysis, or we have also the biggest one. This hammer, you can use this hammer for large or EV structures, and of course the biggest is the hammer, and the smaller is the frequency band that you can cover. Then of course the accelerometers and the hammer must be connected with the SCADAs. This is the data acquisition hardware, the SCADAs mobile with just 8 input channels, but they are enough for us because in our case we have just 3 axial accelerometers, so 6 channels in total, plus of course the channel for the hammer, and then the SCADAs is connected via Ethernet cable with the computer. And that's all. As I said at the beginning, the setup is very simple. So I go to the computer and we're gonna perform the analysis together.
Well, this is the impact testing environment solution suitable on TestLab. As I explained in the previous video, all the software packages of TestLab have the same layout. So you can see here in the bottom the flow chart with all the section that we have to follow in order to perform the analysis. This is the navigator, so the main section, and we are ready for performing our analysis. The first step is to create the geometry file, or maybe import the geometry file. So we go here in the geometry section. This is our component that I already import for you. As you can see, if we go on nodes, we have all our points that go from 1 to 36. We have some points along the circumference of the first flange, other point along the other flange, and other points here in the middle between the two flanges, and other in this face between the spokes. Okay. um, of course, in order to create your geometry, you should insert the coordinate. That means to insert the coordinate of each single point with respect to um, the origin of our global coordinate system. That, if I remember during the introduction, I said that I put the origin of our absolute reference frame here in the middle of this face of the rim. So you should go on your structure and measure the distance of each point with respect to the origin, and of course insert here the correct value in x, y, and z, of course in meter. And then if some point require the Euler's angles, you have to insert also the Euler angles. So if I go on model nodes Euler's angles, probably is better to view XY. Okay, there are some points in the geometry, especially the points along the circumference of the rim, that need the Euler angle definition, especially the point that are along the bisectors of our reference frame. So you have to go on the structure with a goniometer, for instance, measure the angle mismatch between the local coordinate system, so the system of each point of measurement, with respect to the global coordinate system, so our absolute reference frame, and of course insert the correct value here. Okay. Moreover, if I go on components, you can see that I have also add some surfaces. So if you go on surfaces subsection, you can see all the surfaces that I have added, just to make clear our geometry. If you, of course, you want to import your geometry file, you have to search it on the menu here on the left, and then click on import, and you can import your geometry file. Now that we have done our geometry, we can skip on channel setup section. Here we have to define the channel setup parameters. Here on the left, you can see all the inputs of our SCADAs, that are 8, but we will use just this 3 input for the first accelerometer, other 3 inputs for the second accelerometer, and the last one is for the hammer. So if I click on show on, I just show you the enabled input. So we have to write here the name points, that if I skip on use geometry, you can see we have the first accelerometer here in 0.1, and the second instead is in 0.30. So we put 1, 1, 1, the 3 direction of our 3-axial accelerometer, and 30, 30, 30. Okay, about the direction, you know everything, so we have to select the measure direction of your accelerometer, depending, of course, in the way that you have attached the accelerometer with respect to the global coordinate system, of course. Input mode, all our sensors are ICP. Measured quantity is, of course, acceleration for our accelerometers, and force for our hammer. Okay, the actual sensitivity, you have to look the calibration data cards that you find in the sensor box, and you have to write here the right value. Okay, is millivolt per G for the acceleration quantity, and millivolt per Newton for the force. Okay. Just the last thing, of course, for our hammer, we have to switch on the reference button here, of course, because our hammer is the reference point for the analysis. And about the point and the direction of our hammer, here you can put whatever you want, because as explained you in the following, we will use the hammer-based run name, that is a procedure that automatically change the points, the name points, and the direction of our hammer during the analysis. Okay, so I've already said everything about the channel setup. We can go on the impact scope section. Here, in the impact scope section, we have just to define the scope settings, so the setting of our acquisition, the acquisition data. We have the bandwidth and the spectral lines, and of course, depending on the value that we choose for the bandwidth and the spectral lines, we have our resolution and the acquisition time. 3200 for the bandwidth for our frequency range is okay. Also the spectral lines, so we have a delta f for 0.78 Hz with an acquisition time of 1.28 seconds. Okay, so let's move on impact setup. And here we are. As you can see here on the top, we have other subsection to do, the trigger one, the bandwidth, and the windowing. Let's start with the trigger subsection, in which we have to, of course, to define the trigger and the pre-trigger. So the first step is to click here on Start Scope, and then I move on the structure and hit several times our structure. As you can see, that are our impulses. Okay, now I come back and click on Stop Scope, and then Apply Suggested. With the Apply Suggested button, of course, the software gives you the suggested value for the trigger. That is that one, in volt, of course. That is this threshold. If I zoom here, you can see this is our impulse, and this is the trigger level. And the pre-trigger in second, of course. So if I zoom, and maybe single cursor X, 0. This is the pre-trigger time, okay? Now that we have set the trigger and the pre-trigger, we can skip on the second subsection, the bandwidth. Here we can check the frequency range covered by our impulses. So if I go here and I click on Start, and then with the hammer hit a single time our structure, and click on Stop. Okay. You can see here the PSD of the input, the force, okay, in Newton,
of course, and here instead the PSD of our accelerometer. Well, this display say to you that the energy level of your impulse, it's okay more or less till 2 kilohertz, and then if you go the PSD decay till to 0, there are this ripple here, and so probably above the 2 kilohertz you cannot correctly excite your structure. Okay, then we can move on windowing. In this subsection we have defined the window of the input, so our force, and the window of our responses. About the input, we can choose between uniform force and force exponential. The force exponential is the best choice for us. Instead, for the responses, we have uniform, that stands for no window, and exponential. So if I click on apply suggest, here we have the suggested value for the two window. As you can see here, these two displays are for the unwindow input. I can zoom here. And this is for the unwindow responses, so you can skip in all our acceleration measurement. These other display are instead for the window input. This one and this one. This is in time and this is in frequency. So this is the PSD of our impulse. I can zoom here to show you how it is the window impulse. Instead, these other two display are for the window response and the PSD of the window response. You can, of course, move the cursor to change the window, also here. Anyway, if you increase the exponential window here, of course you are denoising your signal. It's okay for the leakage. You are make clear your PSD here, but pay attention that you are not cutting the signal on the top here, because otherwise you are of course compromising your responses. So I click again on apply suggest. With the impact setup section, we have done everything, so we can skip on the measure section. And here we are. This is the measure section. We can go directly on all settings just to have a look of all of them. We have here the acquisition setting that we have import in the impact scope and impact setup, or the triggers, the windows, okay, and we can choose other settings, for instance the FRF estimator. We can choose between H1, HV and H2. The H1 is okay. We can put here our averages, maybe 3 for just to show you how it is. The procedure is okay with implicit accept. The format and the scaling of the spectrum, RMS or peak, the cross power, so power, PSD or power, and so on. But the most important thing here is that one, so the run name option, the hammer based run name. And what does it mean? Here on the right, if I go here, in points hammer, I have to put the name of the point that I want to impact. So we start with point 9 and the direction. The direction, our direction is minus y. It means that we start with this point in minus y direction. So the vertical direction, okay? And due to the hammer run name option, if I go on to the channel setup here, in name and direction of our hammer, you can see that there are 9 and minus y. If I change, for instance, and I put, I don't know, 18 in minus z, for instance, that is this point, and I go to the channel setup, okay, the software automatically change the name of the hammer, the point name of the hammer, and the direction, okay? So we come back here on 9 minus y, and we start with the analysis. So I can click on start and impact our structure in point 9. Okay, just a second that I put 3 limits just to better show you the result. Okay, so now in this 2 plot, as you can see, we have the impulse, okay, our input in time domain and in the frequency domain, so our PSD, the PSD of the impulse. If I put a cursor, as you say before, more or less 2K is the acceptable ranging for our impulses. On the left here we have our responses. You can skip between them. This is okay, this is the time domain and this in frequency domain. Instead, here we have the instantaneous FRF, and here the average one, and here the coherence. Of course, we have done just one impact, and therefore the instantaneous is the same of the average one. Here the coherence, that for the first impact you cannot visualize it, and so I perform another impact. And okay, so now you can see here that we have done 2 averages, one is left. Of course, something is different in the average FRF with respect to the instantaneous one. And now we have also the coherence value. As you can see, the coherence is 1 for the entire frequency band, and of course decrease when we have an anti-resonance. This peak is of course a resonance of our structure. You can see by looking the phase plot here, there is a deviation about 180 degrees. And now I want to show you what happens if I wrong impact the structure. As you can see, there is a warning message, double impact detected. It means that our software is capable of, auto-reject some measurements when detect something wrong. So if I click on OK and I repeat my impact, now I've done all our 3 averages, 0 left, and therefore the measurement of point 9 is completed. Now I should impact all the other points. Anyway, I don't want to show you the impact of all the points because I mean the procedure is exactly the same point by point, and therefore with the measure section we have done.
Now that I have hammered all the possible points, we can see here all the measurements. So if, for instance, I open point 3 and I go on FRF fold, you can see here we have the 3 FRF of accelerometer 1 with respect 0.3. So when I hammering the 0.3, and accelerometer 30 with respect to the hammering 3. Okay, I can of course plot them in a both diagram. Okay, this is the format in the load scale. Okay, but if you want, you can skip in real and imaginary, or if you want, you can display your FRF with a Nyquist plot. Okay, so now we are ready for post-processing our data and to perform the modal analysis. So we have to add in our tools. We go on modal analysis for the, of course, the LSE estimation method, and in Polymax modal analysis for Polymax, we click on OK, and then just a second. We have here in the bottom in our flowchart our new section. Of course, the first step is the modal data selection in order to create the FRF set. And then we can use the time handoff, so the LSE estimation method, and then the Polymax one. And at the end, we can validate our result by the use of modal synthesis section and modal validation. Okay, so let's start with the first step. So we go on modal data selection, and we got a warning message here that says there are many more inputs than outputs. You might want to switch the FRF table. I click on OK. Okay, I mean, this message is because we have 52 references here that are our hammered points, and just 6 responses here, our 2 3-axial accelerometers. So if I click on switch, now we have obtained 6 columns of the FRF table that is a valid data set um, for test lab. Now I can create my FRF set. In this case, I take all the measurements, so H1 and H30. I click on create, and I have created my FRF set. I can of course select click on selected FRF and click on sum just to display my data here. Okay, but I can also for instance, if I click on exclude, in this case, as you can see, the measurement of the accelerometer 1 became red. It means that if I go here, my FRF set, I can create 30. I can create a data set with just the measurements of acceleration 30. I can do the same with, sorry, exclude. Okay, I can do the same with accelerometer 1, create. Okay, just because maybe we want to perform the analysis take into account just one single 3-axial accelerometer at a time. Okay, now we have already create our FRF set, so we are ready for performing the modal analysis. Let's start with the Polymax, and here we are in the band subsection. As you know, there are other two subsection to do, so the stabilization and the shapes. If you go on change modal data selection in existing set, here you can see all the FRF set that we have done. So the one with just the measurement of the accelerometer 30, or the one with just the measurement in the accelerometer 1, or both. Okay, so we can take this one. I click close, so we perform the analysis with just the measurement of the accelerometer 1, so in point 1. As you can see, the measurement of point 30 are red. Here, if I click on selected function, I got all my FRF. Okay, this is just the FRF sum, and in this subsection I have just to define my frequency band, so we can perform the analysis from 300 to maybe 1800. Sorry, I put 10. Okay, just to analyze these peaks, so are 5 peaks, and then we can skip on stabilization. As always, the stabilization diagram of Polymax is clear without any computational poles outside the peaks. And so let's start with selecting our stable poles for the first peaks. Okay, here, as you can see, there are two different lines with stable poles, and so I mean, basically, in normal case, if you have just one peak with two different line of stable poles, probably are computational poles, and the other is the real stable poles. So in normal case, I just take one of them. In this is a special case, and so I take both, and you will understand maybe later the reasons. So I can skip to the other peaks, and another time we have two different lines, and I take both of them. Okay, here just one, and here both. Okay. So now we have selected 9 different stable poles with different frequencies and their damping. We can skip on shapes, and here we have to calculate our mode shape. So this is our stable poles, and we choose as real in order to have real modes, so normal modes. As name, we can write poly real one. Okay, then I click on calculate, and here on processing we have our processing. So this is our first mode. I click on animate. Okay, as you can see, it is a bending mode of our rim, the backside. Okay, but I want to show you also the second mode. Maybe it's better to put here and here. Click on animate. Okay, so now if I go on views, Okay, here on the left we have the first mode, on the right the second mode, and as you can see, these two modes are two normal modes, two orthogonal modes, so two different mode shapes, and this is due to the axisymmetric structure that we have. Our rim is of course an axisymmetric structure, and in the case that you have a sort of symmetrical geometry, you always have two different normal modes more or less at the same frequency. And this is because in the stabilization diagram, we have in the same peak two different lines of stable poles. Okay, and this is because I take both of them because they are two different normal modes. Ideally, of course, they should have the same frequency. Anyway, probably due to I mean manufacturing imperfection, they have just few hertz of difference. Okay, so we can display also the third mode and the fourth. Okay, as you can see, are two normal modes with just 2 hertz of difference. Okay, then we can skip on the five modes. This mode is a pumping mode of this face of the rim, as you can see. Okay, then we have mode 6 and mode 7, other two axial symmetric mode shape. In this case, probably they are not two different mode shape, because here probably these are the same mode shape. Yeah, if I go on the stabilization diagram, so that one, yeah, yeah, probably they are not the different mode shape. Anyway, we can check at the end during the modal validation analysis. And then the last one, okay, these mode shape are axial symmetric. Okay, now we have done the modal analysis procedure using Polymax. We can do the same by using the time MDOF, so the LSCE estimation method. So here we are in the stabilization, sorry, in the band subsection, and we have just to select our bandwidth. So this is okay. That is the same of the one that we use for Polymax. Here we have our FRF set with just the measurement of the accelerometer in point one, and then we can skip on stabilization. And here we are in the stabilization diagram of the LSC tools. As you can see, of course, the diagram is more confused than respect to the one of Polymax. So we can select our stable poles. Once again, we have two different lines of stable poles for the same peak here. Then move on the second one. We take this one and this one. Okay. Then yeah, yes. Okay. This is the peak that probably we have some problem. Anyway, we can try to take both of them just to show you what happened during the validation of our modal result, and both of them. Okay. So once again, 9 in modes in total. We can skip on shapes, and we calculate with the real. So now we are in this one. We click on calculate, and right, just a second that they put the markers here and the names. Okay, I don't know why it's changing the view. Okay, so probably it's better to increase the frame cycle. Okay, so mode 1 and mode 2 as before, mode 3 and mode 4. Okay, the pumping mode of this phase, and then once again we can try to view if something is okay, and then the last two. Okay, now we have done the analysis also with the estimation method LSC, and therefore we can skip on modal validation in order to validate our modal result. And here we are. Here we can activate our process. So the LSCE or the Polymax one. We start with the Polymax. Here the estimated modes. So if I click on animate, okay, this is the first mode, the second one, and so on. Okay, but what we want to do is to see the automac and the complicity. So if I click on automac and maybe I put matrix, okay, this is the automac matrix. As you can see, we have 100% here along the diagonal and low level on the off diagonal term, but here we have some problems that, of course, less than the 30% of automac is an acceptable result. But anyway, something there is between mode 6 and mode 7. So probably a more detailed investigation should be done here. And then if I go on complexity and I put the table, in this case we have a very good result because the MPC is very high here, and the MPD 0 degree with a low scatter. So very good result for Polymax. If we consider the LSCE, the same result. Instead about the automac, yeah, more or less the same result. In this case, the correlation between mode 6 and mode 7 decreased to 80%. And therefore, the last process that we can done is to compare the LSCE with the Polymax by using the Mac. So LSC is here, and here we put Polymax. We click on Mac, then view, top, and we have our Mac matrix that compare the A-game vector estimated by using the LSC tools here and the one estimated by using Polymax. Globally, we have obtained very good result, as you can see. more or less uh, 100% along the diagonal. Of course, we have correlation between mode 6 and mode 7. Anyway, we could repeat the analysis by selecting maybe different stable poles and watching what happened during the post-processing. Anyway, for us, in our case, we can consider our analysis completed. So thank you for the attention.